Yeah, also I thank for the organizer of having me. So I didn't have the privilege to work with Patrick, unfortunately. This is not projected, actually. How do I switch? But I have a personal story I'd like to share. So I didn't really share that story only with my closest collaborators. So most of the talks today were referencing Patrick's paper from 77, Popol, on the abstract interpretation. And I do agree it's a seminal paper. But when I started my PhD, I used another paper, same year, but it was automatic synthesis of optimal invariant assertions. And that's kind of defined what I do in my PhD. For me, A was abstraction, but with the purpose of automation. E or I was indeed interpretation, but whenever I talk about interpretation, was like really fixed point analysis, inductive invariant generation, so induction. So that's the AI for me was abstraction and induction. And I mainly worked in probabilistic programs on one part of my, or mainly worked on polynomial programs. And very recently we started this project on polynomial probabilistic programs, where you don't really have exact inference. You have a probabilistic choice, which is pretty much capturing natural behavior. You just sometimes make a random choice, or you make a probabilistic inference in your action. And I actually think that most of the A and I approaches that have been developed for non-probabilistic programs can be reused in the probabilistic setting. It just, maybe the math is a bit more complex because you have to have statistics inside. So let me just tell you some examples. And really we started this work in 2019 with my colleague Ezio Bartocci and my PhD student Miroslav Stankovic. And I give you a very simplistic view of a probabilistic program. And what I mean here by this assertion, or this assignment here, so I write this constant in a setting that throughout this loop execution, I update the program variable x by making pretty much a non-deterministic choice in this case. So I choose the probability 1/2 to update x by x minus 1, and with probability 1/2, I update it, so I increment it. Now, this is very simplistic because I can actually have here different probabilities, okay? I can have here 2/3 or 1/4 or whatever, but for this case, it's pretty much what I encode here is a so-called random walk. Okay, I just, non-deterministically, I choose either go to the left or I go to the right. And then the question would be, okay, what is the behavior of this probabilistic loop? And what actually means to have a behavior? What is the functional property of a probabilistic loop? So in the non-deterministic case, you always have an so for an input, you have an exact output. But in a probabilistic case, it depends on the choice of the probability you are doing here, depends on which choice you take to execute. So one way to answer, okay, what is the behavior of a probabilistic loop is to view the probabilistic program as a stochastic process, where actually when I talk about what is what is the expected value of a loop variable? Or what is the expected value of a particular variable? It's not the exact value, right? So it's expectation. It's an expectation operator. And in this case, so I just denote the expected value by E. I mean, the expected value, since I take the same probability either update or increment, the expected value would be the initial value of x, which is 0. Now, it's known in statistics that expected values will not describe you the full distribution you can get through executing this probabilistic program. And let me just showcase to show you why expected values are not enough. It's good, it gives you information what can you expect on average, or in terms of expectation from a loop variable. But if you really want to understand what is the behavior of a probabilistic loop, my point is that just like in probability theory, you need more than just expectations. You need so-called higher order moments. Expected value would be the first order moment. And if you really want to describe the stochastic process, you need to have more moments. And let me show you why. So for instance, it's another example. It's a bit slightly more, it's artificial example. It's slightly more complex update. It's still a linear update. And same probability, I either do the left or I do the right. Now, the expected value of this program for x, so the expected value of x in this program would be still 0, because I pretty much do the same. So what you can say, okay, well, in both programs, I have the expected value of x being the same. But the programs are actually not the same. They really define two different stochastic processes. And just to get how different they can be. So here's something, a histogram that we just executed the program, actually that's like 10 million times for 300 iterations. And we just collected the data that we get it from concrete execution. And just by sampling, you can see that the left-hand side plot is very different than the right-hand side plot. So the values, how these program variables are taking are different. Yet, the expected values would tell you, well, they have the same value. So how can you actually notice the difference between the different distributions? And that's exactly what higher order moments, or like first, second, third, and so on, moments will tell you. Now, of course, it will be too easy to answer the first question just by saying I compute you 3 or 4 moments and I have the exact behavior of the probabilistic loop or a stochastic process. Because unfortunately, there are distributions with infinite moments. So even if you describe, let's say, k moments or 5 moments, it doesn't mean that you can completely recover the functional behavior of the probabilistic loops. So that would be like the biggest challenge, how can we really recover or estimate the value distribution of the program variables? And really, I think so one can tackle this problem very similar to how people would do it in applied statistics, that compute higher order moments. View probabilistic programs as stochastic processes and compute their moments, and then use statistical approaches to approximate the probabilistic process. So for instance, well, I had to refresh a lot in my statistic courses, but there are approaches like Gram-Charrier expansion or maximum entropy expansion, which if you give you k moments, it kind of approximates you the complete distribution, but of course with an error. So, but what I wanted to convince you that actually there is one mapping that it's quite natural to do. And with that mapping, you reduce the problem of computing invariants or approximating probabilistic program distributions by really doing abstraction and induction over polynomial programs. And the trick is that we do the induction over the higher order moments of the program variables. So instead of working with concrete values, we work with higher order moments. And what we can actually automate, our abstraction works in terms of automation for a class of so-called prop-solvable loops. And this notion is really coming from the work of Deepak Kapoor and also Helmut Seider, that there is this notion of solvable non-probabilistic loops for which computing the strongest polynomial invariant is decidable. So now we want to have a very similar approach for a probabilistic setting where we can compute the strongest higher order moment and have it decidable. And the trick is that these solvable loops will give us linear recurrences or linear sequences with constant coefficients describing the higher order moments of the probabilistic program. And so that things can get a bit more complicated. So the point is that you can do the abstraction and you can do the induction over higher order moments. You can use our approach, which is in TACAS 2020. And we can automatically compute, let's say, the first order moment of this program. So the first order moment of S at iteration n. So it's a parameterized function in terms of n, the loop iteration. Variance is kind of gives you the second, it's computed from the second order moment of the program variable. And again, in this particular program, if you only compute the expected value of S, they will be the same, but the variance would already look different. So it would give you a bit of intuition that the two programs should be different in terms of probabilistic distribution. So let me just tell you what are these prop-solvable loops, but to stress, okay, that the abstraction, what we're going to do in a prop-solvable setting is that, or the probabilistic polynomial setting is, we abstract loops by C-finite recurrences, or by linear recurrences with constant coefficients. Except that these linear recurrences over constant coefficients, they will be over the higher order moments of the program variables. And then you do induction, you can use anything that you had so far from static analysis, because all you have to manipulate the linear recurrences of the higher order moments. Now, the reason why we have this so-called C-finite recurrences, because this is a very nice class of recurrence equations. They always admit a so-called closed form representation. So they always have a fixed point representation, which is computable. So what we do, we compute closed forms of moments, and then we get a so-called moment-based invariant. And these moment-based invariants can be used to give you the quantitative invariance of the program. So what are these probable loops? Well, we have loops with while true in the very simplistic setting, so you can execute arbitrarily many times. You can have initial values as being defined as concrete constants, so they are over reals. You can have random variables, or you can just have symbolic constants. Then, now here's the thing, but in order to make this automatic, we have constraints on the updates that we can handle. So when you have probabilistic branches, then the update should be so that the variable that you recursively update should be linear in itself and polynomial in previous variables. So you kind of have a triangular structure on the polynomial probabilistic loop. We can use common distributions, such as, for instance, random or uniform distributions or Bernoulli distributions, up to the point that for those distributions, their moments are known. Because if we don't know the moments of the distributions that we are using as parameters, we cannot compute moments for the loop. Yet our distribution can also use symbolic parameters. And then ideally what we want to do here, well, pick a variable, whichever you want, or you can pick all variables, and say compute the higher order moments of that variable. And how it goes? It comes now the issue that now what we have this so-called probabilistic update. And we know from statistics that if you compute expected values of various monomials, you get already good information. However, as I showed you before, it's not enough. So you need to go beyond expected values, because what we are having actually, you just use many things from statistics. If you want to compute the expected value of xi, by computing the expected value of this probabilistic update. And you just do many things so you pull out addition, you pull out constant expectation, and you can write the expected recurrence or the stochastic recurrence of this expected value of xi as this recurrence equation. Now, here are the things from statistics, this we know. So we just use very known properties. That's the problem. If you have two random variables, the expected value of two random variables, if you take them the product, it's not the product of the expectations. So you have to manipulate further. And I just show you. So this would be actually our, if you in computatorics, we know how to solve this kind of recurrences. This is Fibonacci recurrence, so computing Fibonacci sequence. It has a nice closed forms with the golden ratio. Now, in the case of stochastic recurrences or expected value recurrences, this is the recurrence equation we would have. So what does it mean that you have a recurrence equation with a uniform distribution? And what we say, well, you can compute. So use this kind of rewrite rules that are given here to compute the expected values of the polynomially updated variables. And how we do it? So in this case, right, the expected value of xn plus 1 is the expected value of xn plus the expected value of the uniform distribution, which is 1/2. So I just pull out the plus operator. When I want to compute the higher order moment, second order moment of x, I need to compute the expected value of x squared. But now you cannot say that the expected value of x squared is expected value of x multiplied by expected value of x. This doesn't hold in probability theory. So what you do, you compute the expected value of this equality in a quadratic case. So you have expected value of x squared plus 2 times expected value of xn plus 1/4. And then the point is that now you take this expected value of x squared as a recurrence sequence. And you just solve the recurrence over expected value of x squared. So now you have a linear recurrence where you consider the expected value of x as being a sequence variable. I wanted to show you the approach, but it's pretty much a lot. But the point is that what I want to stress, so you can reason about polynomial programs, probabilistic programs in different ways. And the approach we are proposing is that reason about their higher order moments by going from a probabilistic program into a program manipulating expected variables or expected values of variables. And when you have a program manipulating expected values of variables, you just back to the non-probabilistic setting. So whatever you have before from static analysis, you can reuse it here. right, so it can go, things get very complicated or very, very complex polynomial equations. But by these equations, what they tell you, you can just compute expected values of all program variables that you had before, as long as our program variables are from a loop which is so-called prop solvable. Maybe something more can be done, but we don't know yet. So this is a thing for which we have a so-called decidability result for computing higher order moments bounded up by a particular moment, the kth moment. So I think actually probabilistic programs or probabilistic programs, doesn't have to be a polynomial, but we know how to handle polynomial ones. They bring together, as before we had program analysis, linear recurrences, but you also have to use statistical methods to characterize the programs as parametric distributions, probabilistic distributions. The invariants will be not over exact values, but they will be over higher order moments of variables. So far we are limited. In a sense, we have no loop conditions, and we have very restricted multiparts in the program. And then with this, actually, you might think it's very restricted, but you can do many things in Bayesian networks. You can do dynamic Bayesian networks where you can have probabilistic inferences. What is the probability for a Bayesian process that it's not going to rain? Then you would define this as a probabilistic program, and you can encode it as a prop solvable loop. And actually, it can also go for termination analysis. So we have ranking functions in a non-probabilistic setting. Now, in a probabilistic setting, if you want to do termination, things get a bit more complicated. You talk about so-called almost sure termination, and you don't have ranking functions, but you have so-called ranking martingales. And you can compute the conditions for ranking martingales, again, by doing the same thing as you had for non-probabilistic analysis, yet over higher order moments. There is a lot to be done. I only put here, so synthesis and optimization. I mainly talk about the last one, in the sense that you might think actually prop solvable are very restrictive. Well, they are. But you might do a bit of program transformation upfront to translate a program which is not prop solvable into a prop solvable setting. So by just taking polynomial combinations of program variables and reducing the non-nice variables and non-prop solvable variables from the loop. And yeah, with that I would conclude, and I'm happy to take questions.
Thank you so much. Okay, it's time for Patrick's question.
Well, I have seen that you don't handle test. There was test in the loop. I have seen that, and it looks very similar to decidable problem in invariance.
Yeah.
And you have an additional problem, which is that computers do not compute on reals.
Yeah.
And you did not mention that. So you have an opinion on, because people that do probabilistic program, they reason in math and then they go on the computer and they don't study the difference between the two. So do you have some idea on how you could handle this? I don't ask for an answer. So
yeah. So I mean, there is work on semantics of probabilistic programs, and there are extensions of, so there are actually languages supporting probabilistic inferences. So that's pretty much what we are based on, assuming that this is done, and we can already have this nicely represented polynomials or nicely represented probabilistic framework, then we can do the analysis, we can do the inferences. And the rest, I mean, there is actually quite seminal work by Peter Cato and Emma Kyver, who really introduced the probabilistic setting of Hoare calculus and the weakest precondition computation. And then the deductive verification probabilistic programs will be very similar as the deductive verification of non-probabilistic one. In terms of interpreter, like really the computer interpreter, so I would leave it to the programming languages people. I don't know yet.
Not really understood, but I think maybe the floats you can handle them probabilistically. There are floats are very far from other floats are very close, so there is a kind of floats that could maybe model by some probabilistic law and use it.
I don't know. Yeah. I mean, and their approach is like, so if quite many works will just sample. And they collect this big data and they try to analyze or come up with the distribution based on the data. But then it's, then your adequacy, it's quite parameterized to the quality of your data. So if you could have this more symbolic representation, then you could, but it should be actually a combination, because some programs, you cannot do symbolic analysis of big probabilistic programs. That's true. Yeah. Yeah. I agree. Yeah. 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 So because currently we only do so we have the assumption we can represent everything over years, but that's quite a strong assumption.
With your technique.
Yeah.
If you can handle all the book, it's as good as what programmers can do.
No. I mean, unfortunately, quite many programs where you cannot. So it goes beyond polynomial. So you can, for instance, have trigonometric functions.
Yeah, but if you have some exponential, you can take the logarithm and then.
That's true. Yeah, you just don't do it. Yeah.